Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video, I am going to simplify alkene chemistry. In particular, addition reactions of alkenes. I'm going to break down addition reactions into two simplified categories because each of them works in a unique way. So, we're going to break it down into addition reactions with acid and addition reactions without acid. Now, there are plenty of other reactions that you can do with alkenes that we can even classify as additions, namely reductions and certain oxidations. However, those will be covered in another video. Whenever you learn a new type of reaction, it's very important that you go back to the basics, because almost every reaction you'll learn in organic chemistry is based on foundational principles that you should have learned early on. So if you haven't watched my videos on recognizing nucleophiles, bases, electrophiles, and acids, my carbocations video, or my organic chemistry reactions problem-solving process, I highly suggest you go watch those first, because those will teach you the crucial skills necessary to really understand how alkenes behave. This image is a compilation of what I found to be the most important features of the alkene functional group that you'll need to know for undergraduate organic chemistry. Now, the image itself covers things that are far more detailed than what you need to know when you first encounter addition reactions in Orgo 1. Therefore, I'm only going to focus on a couple of features in this image. The first is the pi bond. Pi bonds are regions of excess electron density between two atoms. For that reason, they're nucleophilic and basic. They're also polarizable, and I'll cover exactly what that means and why it's important in future slides. Another feature that I wanted to point out is the left carbon of the double bond. We call that the more substituted vinylic carbon. And this is the more stable site of formation for partial positive charges and carbocations. The reason why the partial positive charge or the carbocation forms at that position has to do with the stabilizing effect of adjacent R groups. If you want more information on that, please rewatch my video on carbocations. With that being said, let's talk a little bit more about the pi bond. Before we get into the reactions, let's review a little bit about molecular orbital theory and how it relates to pi bonds. This image shows a molecular orbital diagram for the pi bond in ethylene. Ethylene is simply C2H4, and there's a carbon-carbon double bond. When p orbitals are found on adjacent atoms, as we have in ethylene, they come together to form pi molecular orbitals. Two adjacent p orbitals that are in phase with each other. In other words, in the image, if we had the red side and the red side of the next p orbital line up and the two blue sides line up, we would say they're in phase. When they're in phase with each other, we create what's called a bonding interaction, where the electrons can take up any space between those two p orbitals. When two adjacent p orbitals are out of phase with each other, we create a node, or a region where the electrons can never be found. When there are more bonding interactions than nodes, the orbitals form what we call a pi bonding orbital, which is lower in energy than the individual p orbitals. So you can see that pi bonding orbital in ethylene below those two p orbitals in the center of the diagram. When there are more nodes than bonding interactions, the orbitals form a pi anti-bonding orbital, which is higher in energy than individual p orbitals. This energy diagram shows the bonding and anti-bonding pi molecular orbitals for ethylene. There are two electrons found in the p orbital system of ethylene, one from each of those carbons. Together, they're going to fill the pi bonding orbital, which occupies the entire region above and below the molecule. The reason why I wanted to show a little bit about molecular orbital theory is because I wanted to emphasize the fact that when you have a pi bond, you have two overlapping p orbitals, and the electrons in those p orbitals can actually occupy any of the space between those two atoms. This shows the normal view of the pi molecular orbital in propene. Because the pi electrons are free to move throughout the pi bonding molecular orbital, it is easy to polarize the bond. So in the presence of a magnetic field, you can see that we can actually move the electron density further to one side or the other of that pi bond. That means that dipoles can be induced in an alkene by electrophiles and acids. In other words, positive areas or regions of low electron density in other molecules. Not only that, but they can also be induced through London dispersion forces, especially from electron-rich species such as oxygen and the halogens. This creates a unique situation where an alkene can act as both a nucleophile and an electrophile simultaneously. In asymmetrical alkenes, the partial positive charge tends to form on the more substituted carbon, as the increase the number of R groups donate electron density to the area, stabilizing it. Now that you have a better understanding of how pi bonds actually can behave, we can start getting into the reactions. Alkene additions, they're reactions involving the destruction of a pi bond to create two new sigma bonds. Generally, the presence of a pi bond indicates an addition reaction is possible, with aromatic compounds being an exception. The two atoms involved in the pi bond do not need to be identical, which means that, for example, a carbon-carbon double bond and a carbon-oxygen double bond both can undergo addition reactions. The end result of an addition reaction is that two new groups are added across the pi bond, with one group being added to each atom involved in the pi bond, as you can see here. Addition and elimination reactions can be thought of as opposites, which means that addition and eliminations are often reversible, and the reactants and the products form a dynamic equilibrium governed by Le Chatelier's principle. Lower temperatures tend to favor addition reactions, while higher temperatures tend to favor elimination reactions. Most of the reactions shown in the rest of this video, therefore, are going to be carried out at low temperatures, usually below room temperature, but it could be even lower than that. As I mentioned in the beginning of this video, we have two types of additions that we're going to focus on: additions with acid and additions without acid. It's much easier to understand alkene additions if we break them into these two categories. Alkene addition reactions with acid follow a carbocation mechanism. We always generate a carbocation when an acid reacts directly with an alkene. And of course, anytime a carbocation is generated, carbocation rearrangements and stereochemistry have to be considered, as I cover in detail in my carbocations video. Generally, there are two types of alkene additions with acid that you'll learn: hydrohalogenation, shown on the left, and acid-catalyzed hydration, shown on the right. Now, I'm about to go on a little bit of a tangent here, and there's this outdated concept that is still extensively taught and tested on, unfortunately, and it's called Markovnikov's rule. And it's based on an observation from the 1800s that hydrogen is typically added to the least substituted side of the pi bond during hydrohalogenation. And you can see that on that left image. While Markovnikov's rule for hydrogens applies to several different addition reactions, it doesn't apply to plenty others. And of course, we creatively call these anti-Markovnikov. Now, when it comes to alkene addition reactions, having a foundational understanding of basic principles will be far more useful than memorizing whether every single addition reaction is Markovnikov or anti-Markovnikov. But many organic chemistry courses, to the detriment of your ability to actually solve and work through things logically, still emphasize learning random facts such as whether something's Markovnikov or anti-Markovnikov over actually understanding why reactions work the way they do. So for the rest of this video, you're going to actually learn how the reactions happen, and you'll actually understand why the reactions happen. So you should never need to memorize any of this crap ever again. Now that my rant's over, we can actually go ahead and try to understand hydrohalogenation. And to do so, we're going to look at this reaction using the organic chemistry reactions problem-solving process. So the first thing we're going to do is analyze the functional groups on the very first reactant. And this is an alkene. At this point in your organic chemistry career, you don't know a whole lot about alkenes. We know that there's a pi bond, and because there's a pi bond, we should know that it is both nucleophilic and basic. And that's because there's extra electron density in that pi bond. And at this point, you should also know that the primary reactions that pi bonds undergo are addition reactions. Sometimes you also learn you can do reductions and oxidations around the same time that you learn about the addition reactions, but for the purposes of this video, we know for sure these things. Next, we're going to look at the second reactant, and that is HCl. And if you remember from Gen Chem, HCl is a strong acid, so we're just simply going to write that we have an acid right here. Now that we've identified everything we know about both the alkene and the acid, we can start drawing our mechanism. We know that we have a basic pi bond, and we know that we have an acidic hydrogen. And in chemistry, we draw arrows from negatives to positives. So we're going to draw an arrow from the pi bond to the partially positive hydrogen on the acid. Of course, when we do that, we are breaking the pi bond. We're making a new bond between one of the carbons on the pi bond and the hydrogen. And since hydrogen cannot have two bonds, that means this chlorine has to be broken off from the hydrogen. And that's going to leave us with a dilemma. Which carbon gets the hydrogen? Well, there are two choices. We can put the hydrogen on the left-hand carbon, or we can put the hydrogen on the right-hand carbon. But once we add that hydrogen, another question should be raised. Since we're breaking a pi bond, we're removing that fourth bond from both the left and the right-hand carbons. Only one of those carbons is getting a bond back, which means that the carbon that doesn't get the bond to the hydrogen gets nothing in return. And if it gets nothing, what does that give us? Well, that would give us a carbocation. To help you visualize the electron flow in this reaction and also help you understand why the second choice is the right choice, I have two diagrams to show you. The first diagram is right out of my carbocation video. The more R groups you have attached to the carbocation, the more stable the carbocation is. A primary carbocation is so unstable that it can't even be formed in this reaction. That's why that top carbocation is not going to be created in this reaction. So we can go ahead and erase that one. The second diagram comes directly from this video. Remember earlier when I said that the pi bond in an alkene is easily polarizable. That means that when we have a partial positive hydrogen in HCl, that's going to attract the electrons from the pi bond to it. So you can kind of see where I have increased electron density getting pulled towards one side of the alkene, and that's the side that we're going to attack the hydrogen from. And you can already see that that partial positive charge is forming on the more substituted carbon. So this is the same idea here, where the hydrogen gets added to the right-hand side, and once that bond officially breaks and makes the new bond to hydrogen, we're going to have a carbocation left over. And this visualization really helps you see and understand that process. Of course, we're not quite done with this reaction because we still have the chloride anion that's left over from that first step. And this is where the reaction becomes really easy. The chloride anion has 4 lone pairs, and it has a negative charge. So to continue with our theme of drawing arrows from negative charges to positive charges, we're simply going to draw an arrow from the negative charge, or one of the lone pairs, over to the positive charge on the carbocation. And that puts the chlorine in this position on the left-hand carbon of the original double bond. I'm going to draw on that hydrogen just so we can see the addition product where we added both a hydrogen and a chlorine across the double bond. Of course, you wouldn't need to draw that if you were taking a test because we don't need to draw hydrogens on carbons. Overall, in this reaction, the key idea is that the carbocation is going to be generated at the more substituted position because that is the more stable position. Memorizing where the hydrogen goes misses the point. If you understand core organic chemistry concepts, such as carbocation stability, you will understand why the reaction happens the way it does, and that is so much more powerful when it comes to learning organic chemistry. Not all reactions with carbocations are that simple, however. So let's take a look at 2 more examples. In the first example, the pi bond is going to attack the hydrogen the same way it did last time. And of course, we now know that that is going to add the hydrogen to one side, but more importantly, it's going to put the carbocation at the more stable position, just like this. After that, we have the Cl negative, and that's going to come in and go to where the positive charge is. And that, of course, is going to give us a chlorine in this position. Now, if we said this was our answer, we would be incorrect. And that's because if we pay attention to step 4 of the problem-solving process, we need to check our work by considering things such as stereochemistry, resonance, and carbocation rearrangements. Now, we don't have to worry about resonance in this example because when we generate that carbocation intermediate, it's not next to any other p orbitals. So we don't need to worry about resonance. We don't need to worry about carbocation rearrangements either because that is a secondary carbocation, and the adjacent carbon to the right is primary, so we're not moving it there, and it's also secondary to the left, so it's not going to be more stable on the left position either. Now, we do have to worry about stereochemistry. Carbocations are trigonal planar, which means that when we attack them, we can attack them with equal probability from the top side or the bottom side. So that means when that chlorine gets added on, we might have attacked it from the front, which would give us a wedge, or we could have attacked it from below, and that would have given us a dash. Now we have a complete answer. This next reaction starts the same way. We have our pi bond attack the acidic hydrogen, and that kicks off the chlorine. That's going to give us a carbocation in this secondary position. But notice that to the left of the carbocation, we have a tertiary position. And what we can do is do a 1-2 hydride shift. In other words, we're going to do a carbocation rearrangement. So the hydrogen that is in this position right here is going to get moved over to where the carbocation is. And of course, when we do that, now we're going to have the carbocation in this more stable tertiary position. Notice that I also removed the stereochemistry from that spot because now it is trigonal planar, so that methyl group is no longer on a wedge. Of course, once we do that, then we can bring in our chloride, and this is going to attack this carbocation, and as a result, we are going to get this chlorine right there at that tertiary position. Now you may be wondering, do I need to consider stereochemistry? And the answer, of course, is always yes. However, if you note that carbon has 2 ethyl groups attached to it. So in other words, there are not 4 unique bonds on that carbon, and it is not a stereogenic center. So even though the chloride could have added to the front or the back of the molecule, it doesn't matter because we don't have a stereogenic center. So that is our one and only answer. The next reaction of an alkene with an acid is called acid-catalyzed hydration. And like all reactions, we should solve it by using the problem-solving process. So first, again, we're going to talk about that alkene. And we have the same things about the alkene that we had last time, and that is we have a nucleophilic and basic pi bond, and we can do addition reactions. Next, we're going to move on to what's on the line, which is H2O and H2SO4. Now, depending on your textbook, you might see H2O, H2SO4 on the line, you might see H3O+, or you might see dilute H2SO4 instead. All of these things represent the same reaction. What I want to point out is that whenever you have H2O and H2SO4, you make H3O+. So instead of dealing with this, we're just going to cross it out, and we're going to write HOH2 with our positive formal charge on the oxygen because it has 3 bonds and only 1 lone pair. That's the same thing as H3O+. The next thing we're going to do is we're going to label this as an acid. So once again, we have an acid. So now we can draw our mechanism, and just like the other reaction with an alkene and an acid, we're going to have this nucleophilic and basic pi bond. We're going to have it attack this hydrogen, and as a result, that hydrogen-oxygen bond is going to break, and that oxygen is going to get that lone pair. Just like last time, we are generating a carbocation, so the hydrogen goes to the less substituted side because the carbocation must go to the more substituted side, because that's where it's more stable. After this, what do we have left? Well, we just generated a water molecule in that first step. And what do we know about water? Well, water has 2 lone pairs on the oxygen. So as usual, we're going to draw our arrow from an area of high electron density to an area of low electron density, or negative to positive, as we usually call it. What this does is it adds an OH2 to that more substituted position where the carbocation was located. Of course, again, this oxygen is now going to have 3 bonds and only 1 lone pair, so it's going to have a formal charge of +1. So, as is usually the case when we deal with neutral nucleophiles, we do need to have a deprotonation or a proton transfer step, because we don't like that positive formal charge on the oxygen. So what happens is this H2O, or the extra H2O that we have, is going to remove a hydrogen, and that's going to give us our alcohol product, and it's going to give us back our H3O+. This is why we call this an acid-catalyzed reaction, because we don't use up the acid in the reaction, but we do use it in an individual step and then get it back. As is always the case, as soon as we think we have our product, we should double-check our work by checking for stereochemistry, resonance, and carbocation rearrangements. In this particular example, we don't have any of those things to worry about. However, because we did have an intermediate carbocation, that should be our clue that we do need to pay attention to those things. To recap, we've reviewed 2 different reactions of an alkene with an acid. And what's the same about both of these is that we generate a carbocation in the first step of the mechanism. The next set of reactions are going to be different. They don't generate a carbocation, so we have to approach them a little bit differently. Alkene additions without acid never generate carbocations. Therefore, we can never get carbocation rearrangements. We end up getting cyclic or bridged transition states or intermediates during the reaction, and stereochemistry and regiochemistry are going to be unique to each reaction. However, they will be governed by familiar principles. There are several types of alkene additions without acid that we'll cover. The first is Oxymercuration, Demercuration in the top left, Hydroboration, Oxidation, as shown in the top right, Halogenation in the bottom left, and Halohydrin formation in the bottom right. The first reaction we're going to cover is Oxymercuration, Demercuration. This reaction is going to add an OH to the more substituted side of a double bond. You may be thinking, didn't we just do that when we did acid-catalyzed hydration? And the answer, of course, is yes. The difference is, with acid-catalyzed hydration, you generate a carbocation, and therefore your reaction is susceptible to carbocation rearrangements. Here, we're going to be adding the OH without having to worry about carbocation rearrangements. Unfortunately, this reaction has some things to it that are a little beyond what you could possibly ever learn in an Organic Chemistry 1 class. So, several steps are kind of just shown to you without much explanation. Even though that's the case, I'm going to show you the important parts that you're going to need to know. As will always be the case, we're going to go to the problem-solving process. And the functional group on that first molecule is an alkene. And again, we have a nucleophilic and basic pi bond, and we know that we can do addition reactions. Now let's analyze that first reactant on the line, and that is HgOAc2, or mercury 2 acetate. What you need to know about this molecule on a practical level is that it breaks apart and forms an equilibrium with HgOAc with a positive charge on the mercury. How that happens isn't really all that important. What you need to know for the mechanism is simply that we do have that positive charge on the Hg, which makes it an electrophile. So we can go ahead and say that this is an electrophile. So now we can move on to our mechanism. Of course, we have our nucleophilic pi bond and we have our electrophile, so we're going to draw our arrow from our negative to our positive. And just like in our other examples, we can assume that we're polarizing that pi bond and we're going to attack from that less substituted side that starts to bear that more negative charge, whereas the more substituted side, the more stable position, is going to just start developing a positive charge when this attack happens. What we're going to get then is something that looks a little bit like a carbocation, but I will show you why it is not a carbocation in a second. So we're going to put a positive charge here as if this were a carbocation, but I'm going to put a question mark here because this isn't really what we have. And the reason why it isn't what we have is because mercury has a ton of electrons around it. The reason why mercury has a ton of electrons around it is because it's very far down on the periodic table. It actually has electrons in the F and D orbitals, and we don't really learn about those at all in organic chemistry. We're mostly stuck in this sp3 hybrid world for the most part. So this lone pair, it's more of a convenient way of representing that we have a lot of electrons. And as soon as this bond between the carbon and the mercury forms, the excess electron density on the mercury is instantly attracted to this positive charge. So we can represent what's happening as kind of a resonance structure that looks like this. For illustrative purposes, I'm going to draw this as a resonance hybrid. Notice that in the resonance hybrid, we have a partial positive charge both on the mercury and on the more substituted carbon, where we originally had the alkene. The reason why we have a partial positive on that site is because if this were to have generated a carbocation, it would have had to have been at the more stable or more highly substituted position. However, because it's not a true carbocation, we cannot do things like carbocation rearrangements, and we're stuck with this bridged version of the molecule. What this should also show you is that that carbon with that partial positive charge is more susceptible to an attack from a negative charge than the carbon on the right. What happens in the next step, therefore, is this water molecule that we have, which has two lone pairs, is going to act as a nucleophile, and it will, in fact, attack that partial positive carbon, which will break open this ring. Of course, this generates another intermediate where we have a formal charge on the oxygen, so we're going to have another deprotonation step, just like in acid-catalyzed hydration. The most likely species to deprotonate this OH2 is actually the other OAC negative group that we had get kicked off when we created the HgOAC+. From here, we can move on to step 2 of the reaction, which is adding NaBH4. This is the part of the reaction that is completely glossed over in organic chemistry classes. NaBH4 is a reducing agent. Reducing agents add hydrogens to carbons. In this case, the reducing agent is also going to remove that HgOAC. So a hydrogen will be put in place of that HgOAC, completing the reaction. This is actually quite a complicated mechanism to do this, and it involves several steps in a radical reaction. So there's no way that you would ever be required to know this, so all you need to do is trust that we're replacing the HgOAC with a hydrogen. Of course, our discussion of this reaction would not be complete if we didn't talk about stereochemistry, making sure that we do the last step of the problem-solving process. Interestingly enough, both that OH and that H can be added from either side of the molecule, meaning that we can get a wedge or a dash on that OH, and if that right carbon were actually a stereogenic center, which it isn't, we could have also added that hydrogen from a wedge or a dash. The reason why we can add the OH on a wedge or a dash goes back to the original step in the mechanism, which was when that alkene attacked that Hg+. Because the alkene is trigonal planar, we could have actually added on that HgOAC from the top side or the bottom side. And then when the water attacked that carbon, it would have simply attacked from the backside of wherever we added the HgOAc. So because the HgOAc could have been added above or below the plane of the alkene, the OH also could have been added from above or below, or front or back, however you want to look at it, which means we will get an equal mix of both versions, the wedge and the dash, of that OH. While in this particular example, it doesn't matter if that hydrogen was added on a wedge or a dash because we don't have a stereogenic center, it could have been added on either, and that would have been independent of the stereochemistry of the OH. And the reason why is because it involves a radical mechanism, and once you have a radical, it's like a carbocation, it's a trigonal planar carbon, so we could have added the hydrogen again from the front side or the back side. Now that we have our final product, let's recap our key points for this reaction. Oxymercuration demercuration adds an OH to the more substituted side of a double bond without involving carbocation intermediates. If the same starting material were used in acid catalyzed hydration, however, a carbocation rearrangement would have occurred, yielding a completely different product. The next alkene addition that we're going to do without acid is hydroboration oxidation. And just like the previous reaction, there is a step on here, step 2, that you don't really need to know all the details of. So again, we're just going to kind of gloss over them and get you to the final product. In addition, step 1 also has some interesting twists to it. The idea, though, is that I want you to understand why the reaction happens the way that it does regarding the alkene, not necessarily every individual nuance in the reaction. Once again, in step 1 of the problem-solving process, we are going to identify the functional group on the first reactant and make a list of what we know about it. And of course, that again is an alkene. We have a nucleophilic and basic pi bond, and we can do addition reactions. Moving on, we're going to identify the next reactant and make a list of what we know about it. Here we have BH3 in a THF solvent. The BH3 is what we actually care about, however. To really understand BH3, it's probably better that we draw it. And it is a boron bonded to 3 hydrogens. There is no lone pair on the boron. That means the boron, with its 3 bonds, has 6 valence electrons, which means that it is electron deficient, and therefore it is an electrophile. Now the reaction should start to make sense. We have a nucleophilic pi bond, and we have an electrophilic boron. But I'm going to do one more thing to really make sure we understand how this works. I'm going to rewrite BH3 as H2BH. And you'll see why in a second. In our reaction mechanism, we're going to draw an arrow from the negative to the positive. In other words, we're going to polarize this pi bond. The electron density is going to move towards the right-hand side because the partial positive is going to develop on the more stable, more substituted position. So we're going to attack this boron like this. Now, the interesting thing about hydrogen is that it's just slightly more electronegative than boron. And as soon as this bond starts to be made, that partial positive starts developing on that left carbon of the alkene. And that allows the electrons in this boron-hydrogen bond to essentially simultaneously attack that positive charge, just like this. And what that is going to give us is it's going to give us a cyclic transition state. I'm going to draw it on the right. The first thing you might notice is that we actually have 2 transition states. The second thing you might notice is that the hydrogen and the BH2 are both added to the same side of the original double bond. That is, both are added either to the top side or to the bottom side. To understand this, we have to rotate this alkene in a different manner than how it's drawn in order to see why this happens. On the bottom left, I have a top and a side view of the same alkene. The bottom 2 groups from the flat version shown on the left are going to be rotated so that they come towards us. So in a 2-dimensional or side view, they would be viewed as a wedge. Because we're rotating those towards us, the top groups are therefore rotated away from us. So if we were to redraw that as a 2D image, those top groups would appear as a dash on a 2D image. That is the orientation we need to be viewing when we do hydroboration oxidation. When that alkene attacks the boron and that boron-hydrogen bond attacks the other side of the alkene, there's a 50-50 chance to add to the top side or the bottom side of this trigonal planar alkene. And that's why we get two different transition states. Of course, these cyclic transition states are incredibly short-lived, so they will resolve themselves, and we won't have these partial bonds for very long. The products shown now represent the completion of step 1, the hydroboration step in hydroboration oxidation. One of the more important things to note in this reaction is that the hydrogen is added to the more substituted side, which I will regrettably call anti-Markovnikov, and that is because the hydrogen in this reaction acts as a nucleophile, attacking the partially positive side of the alkene that develops when the alkene attacks the boron, as shown in the bottom right figure. The second step in hydroboration oxidation is, of course, the oxidation step, where we add H2O2 and a source of OH- to effectively replace the BH2 with an OH group. The exact mechanism of this oxidation is not something that you likely need to know for any undergraduate organic chemistry courses. Most courses, in fact, would be thrilled to know that this is simply anti-Markovnikov and that the OH goes to the least substituted side of the original alkene. Hopefully now you know why this is the case, rather than just blindly memorizing this and then forgetting about it the next time you see it a few chapters later. So I'm going to go ahead and draw the final products now. Here we have the final products, and you can see that the stereochemistry is maintained throughout the entire reaction, where we have the H and the OH added either to the top side of the alkene or to the bottom side. As you can see, the mechanisms for the non-acid additions to alkenes can get a little bit more complicated than the ones that involve acids and carbocations. Luckily, these next two reactions are quite a bit simpler than the first two. Here, we're going to go over halogenation. So as usual, we're going to start with the problem-solving process and say everything we know about that alkene. And once again, this should come as no surprise. There's a nucleophilic and basic pi bond, and we can do addition reactions with it. Next, we go to what is on the line, and here we have Cl2. And what's interesting about Cl2 is that it is a non-polar molecule. So how are we going to react a nucleophile or a base with something that's non-polar? Well, as I mentioned a while ago now, the pi bond is easily polarizable, and we can polarize it with something as simple as London dispersion forces. We know those chlorines have a lot of electron density around them. Both of those chlorines there have 3 lone pairs. So as the alkene approaches that Cl2, those electron clouds are going to start to repel each other, and that's going to start forming a partially positive and a partially negative side on the chlorine, and a partially positive and partially negative side on the alkene. And once that happens, is we get a nucleophilic attack from the alkene onto the partially positive chlorine. So we're going to draw this just like that. And once again, that's because, let's say this side became partially positive and this side became partially negative. Now, just like before, as soon as that starts to happen, we start generating what seems to be a carbocation, just like in the oxymercuration, demercuration reaction. So interestingly enough, because we do have these 3 lone pairs on the chlorine, one of these lone pairs can then simultaneously attack the developing partially positive side on the other side of the alkene. So do we get a carbocation? Not quite. What we end up getting is a bridged halonium. And once again, we're going to take the side view of this molecule. We're going to draw it just like this. where now we have this resonance hybrid that looks like a three-membered ring where we have a partial positive charge on the chlorine and a partial positive charge on the more substituted side of the original alkene. One thing that I should also show is that when that bond is being formed, we do kick off the other chlorine, creating a chloride anion. Now, before we use that chloride anion to attack that partial positive carbon, I should point out stereochemical considerations. And of course, what I mean by that is when we attack, we can attack from either the top side or the bottom side, just like in the last reaction, because the carbons of the alkene are trigonoplanar, meaning they're flat. So let's draw in the other possibility here. Now that we have this drawn, all we need to do is draw the chloride anion acting as a nucleophile and attacking that partially positive carbon in either one of these. This is going to be a backside attack. It's very SN2-like, and it'll simply go in an attack here, and that will open up this three-membered ring. It can also do it on the bottom one, so I can do a similar reaction down here and open up the ring from this bottom side as well. Notice that in our final products, one of the chlorines was always added to the top side of the original alkene, and the other chlorine was added to the bottom side of it. These stereoisomers will be produced with equal probability, creating a racemic mixture of products. If you understood the halogenation reaction of an alkene, then this reaction, Halohydrin formation, should be really easy for you because it's nearly identical. So of course what we're going to do is we're going to start with our problem-solving process and identify that we have an alkene, and it has a nucleophilic and basic pi bond, and we can do addition reactions with it. The first step of the mechanism is identical to the halogenation reaction. These bonds get polarized, and we're going to have this alkene attack this chlorine, and simultaneously one of those lone pairs is going to attack the partial positive charge that is forming on the other side of the alkene. This is also going to kick off the chlorine, giving us a chloride anion. Just like before, we could have added to the top side or the bottom side of the alkene, and we're going to take that side view to make this easier to understand. Now the next step is where we change things up a little bit. And that's because we're using water this time as a solvent. And water, of course, has two lone pairs on the oxygen. And because the solvent exists in vast quantities compared to the chlorine, it is more likely that the water is going to be used as a nucleophile rather than the chloride anion. So the next step is going to look identical to halogenation, except we're attacking with a water nucleophile instead of a chloride nucleophile. Once again, we'll be attacking the more stable position for that partial positive charge via backside attack, giving us the next intermediates that you can see here. And just like before, when we attack with water, it's a neutral nucleophile, so we're going to end up having too many bonds to it, and it's going to have a positive formal charge. So the next step will be our last step, and that will be the deprotonation step, giving us the halohydrins. Halohydrin formation also happens via anti-addition. Notice that in both the final products, the chlorine and the OH are added opposite to each other, with the OH always being added to the more substituted carbon, because that's where it attacks as a nucleophile. These stereoisomers will be produced with equal probability, creating a racemic mixture of products. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.